Good evening. Welcome to Lecture 5 of Topic 2 of Unit 3, Electrical Circuit Analysis. Now, this is going to be covering the main ideas of Chapter 9.2 of Book 1. However, it is going to require quite a few things that we've done across the entirety of the topic. Okay, this is sort of the culmination of, sorry, I'll just straighten that up a bit, the culmination of the electrical sort of information. So here are your learning intention and success criteria. Please pause the video and complete the knowledge and skills table down here in the bottom right corner. Okay, so we can see here we need to know a couple of laws: Kirchhoff's laws, Ohm's laws, and equivalent resistance. We need to analyse some circuits and determine some unknowns. There's a fairly standard calculate verb here, but there is a new knowledge verb here, identify symbols for circuit components. So first thing, well, we need to know what those symbols are. And the second thing is, well, how do we calculate these values using all these bits of information here? So in our unit, we have looked at a few different ideas, and this last topic is the culmination of all these. I pretty much guarantee that there will be a question about electrical circuits on your final exam. It's almost certainly guaranteed because it hits so many criteria points, and it's such a common sort of example of depth of mastery. So certainly keep this in mind for when we get to closer to your exam time. So let's recap the skills. The first ones were Kirchhoff's two laws. The voltage law, okay, the loop law, where the sum of voltages on a loop must equal 0, and that's the path from one terminal of a battery back to another. And then the second one was the current law, or the junction law, for looking at how current flows in and out of a junction point. So here on our diagram, we can see our battery, our battery here, because there's two cells, and here's a loop from here through R1, R2 back to the terminal. But there's another loop as well, R1 through to R3, and then back to the terminal. And so remember, that implies that if the voltage through here and the voltage through here has to add up to 0, that these two must be equal to each other because they're parallel. The current law, well, the current is flowing out of here, coming through here, gets to this junction, this little nodule here, and it splits. Some of it goes this way, some of it goes this way. While the voltage will be equal across two parallel rungs, the current is not. It could be. If the resistance is the same, it certainly could be. However, it doesn't mean that it is. Sorry, my camera keeps trying to bend itself around. Just because I've been using it for using our Collaborate sessions. Hopefully it stays there. Okay, so these are our first two laws. We had Ohm's law, and that was the relationship between voltage, current, and resistance. Remember, commonly written like this. In the formula booklet, it's written as R equals V over I, and I know Walding commonly uses I equals V over R, so three different ways depending on what you're used to. And in our last video, I believe, we looked at our two equivalent resistance laws. We had our parallel one, where that the parallel resistance is the inverse in summing all those up, and the series where it is just adding them together. So the resistance through this and this, we just add them together. But if we just had the electrical circuit going through R2 and R3 to work out the equivalent resistance of these two, we would have to add the inverse. And then if you get more complicated situations like this, well, if we want to know the total resistance, we need to use a parallel law to work out the equivalent for these two, and then the series to work out the addition of this plus the equivalent of this to get the total. Sounds very complicated, but it's always about taking very, very small steps. So if you have these 5 laws, generally any electrical circuit's just going to be like a puzzle to work them out, work out the missing values by using these laws. So the last bit of knowledge we need is how to recognize the drawings. We need the symbols. These are the symbols taken out of Walding's text. However, these are also the ones, where they are anyway, that match up to the syllabus. So we'll go through them. Excuse me. Here we have a cell, and a cell is when you only have one combination of these small elements. This is a battery, or many cells together, because we have many cell drawings. If you're going to do a student experiment on involving a variable DC supply like our power packs, this is the symbol that you would use. Here we have a switch that is open, and if the line was drawn solid between the two terminals, it would be closed. This is the one for a lamp. Now, there is an alternative one that commonly pops up that looks like this. Do not use that if you're asked to draw anything for your exam. So for the moment, I would really recommend at this point in the syllabus, just use this one. Don't worry about remembering two. Just this is lamp, this is only lamp, love lamp, there it is, okay? Be like brick. If you don't get that joke, go watch Anchorman. Over on this side, we've got fixed resistors. Now, sometimes, and you'll often see me do this when I'm drawing circuit diagrams, is I'll just use a rectangle for resistors. The syllabus has, excuse me, bit of a cough. The syllabus has the squiggly line as the resistor. That is what I expect you to use for your exam. So just think of those as resistors. Here we have variable resistor, and you can see, like over here, this was a DC, a voltage with a variability. That's what the arrow is meaning. And here we have the same thing. We've got a resistor, but we've got an arrow over it, so it's variable. Sometimes you might see it like this because we could feed the circuit back in, like when we used the rheostat. So this is the symbol that you would use for the rheostat generally. And then we have our voltmeters and our ammeters. Now these are on page 254 of the textbook. And as I've said, do not use those other two. I have had a communication with the QCAA director for the physics syllabus. They've said keep to the given ones as a precaution. While you may not get marked down for using these two alternatives I've just drawn, I would encourage you not to worry about it and just stick to the standard ones. Okay, now the rest of this video is going to be going through examples. It will be a long video, so feel free to watch one or two examples, take a break. However, there is an activity at the very end of the video I want you to do. Okay, that looks fairly clear. So here's our diagram. I'm going to have to, because just to save some white space, we're going to have to come back and forth between the questions and these. So here we've got a diagram. So let's identify our bits first. We have a battery, then a point labeled A, then another battery, then a point labeled B. We're told that this is a 2-volt cell and this is a 6-volt cell. We can see the current has been labelled for us. Remember, conventional current flows from the positive, the long line, through to the small line. I'm going to assume that this whole thing is a cell. And we have two resistors here. One's 3 ohm and one is 1 ohm. So let's have a walk through. Here's what we've been asked to work out. The voltage A and the voltage at B. So we're going to start, and you can see here that's where it's labelled 0 volts. I'll just bring up my pen. We're going to start here. So we'll call this point O. So as we go from point O to point A, we see, yep, oh, we've gone through a 2 volt. So voltage at A must equal 2 volts. But then we keep going, because we want the voltage at B. We've gone through another battery. We can see this one is 6 volts. So the voltage at B must equal 2 plus 6 equals 8 volts. Batteries in series are always just added voltage together. Okay, so there's our first bit. Our voltage at A, and then our voltage at B. Okay. So if we were to graph this out, it looks something like here is starts off at 0, gets past A, goes up to 2, gets past B, goes up to 8. Sorry, had a mind blank there. And then as it comes through these resistors, it'll drop and then drop and go back to 0. Please note that that is definitely not to scale. The total resistance. You can see we've got two resistors here, okay, and resistance, they are in series. So the resistance in total is going to equal resistor of 1 plus the resistor of 2. And so we just take our numbers, 3 and 1. equals 4 ohms. Now we need the circuit current. So the circuit current, or the total current, we can use a simple Ohm's law. We know that there is 8 volts being applied in total, because we've got this 2 plus this 6, and we know that the total resistance is equal to 4. So let's see, I equals V over R from Ohm's law equals 8 divided by 4 equals 2 amps, so quite a lot of current. Now, this one here, let's break down the symbol. Delta V30. Okay? Sorry, not delta V30, delta V3 ohms. You might not be able to see the 3 ohms quite clearly, however you can go to the textbook if you wish to. So, what is the delta V at the 3 ohm value? And that's meaning, well, what's the change? What's the use of the voltage? Again, we're going to use Ohm's law, but we're going to use it a little bit differently. We know the current going through here must be 2 amps. We've just worked that out. This is a series circuit, so current must be the same everywhere. If there was a parallel component, then we'd have to work out the change in the current through the parallel parts, but we don't have that here. And we know that V equals IR. We know I equals 2. That's going to equal 3 ohms. So therefore, the change in voltage, how much voltage it uses up here, must be equal to 6 volts. The fact that it just happens to match this is no relevance at all. They could have used 4 and 4, and we still would have got 6 volts being used up as it goes through here. And we want to know the other part, what's the voltage, the change in voltage at the 1 ohm. Now, a couple of ways we could do it. We know that the total voltage is 8 and we've used up 6, so whatever's left over must get used up here. Or we could work it, so it's using Kirchhoff's loop law. In fact, I will write that out. So the sum of V equals 0. So we have, let's see, sum of V equals 2 plus 6 plus, we've just worked out that's using 6 here, that's why I've put a negative, plus some number, let's just call it V, equals 0. That means, cancel all of those and rearrange, V will equal negative 2, or that the 101 is using up 2 volts. Alternatively, we could have used Ohm's law. V equals IR, we know I equals 2, resistance equals 1, equals 2. Now, note, I know this is going to, you might grant, but that's a negative and that's a positive, so which is right? The negative tells me that the voltage is being used up, right? So when you're using Kirchhoff's law, you've just got to be really careful about your signage. Batteries, positive things that give us voltage have to have a positive, while things that use up voltage must have a negative. And when you get really complicated circuits and you've got batteries facing in the wrong direction and you don't know what direction things are going, you just pick one and you make sure you stick to it and go, well, it's going that, I'm going to say it's that way is positive, so some things might end up being negative or some things might end up being positive. It's especially important when you have really weird circuit diagrams with diagonals and stuff. I don't know if we'll get to that level of complexity in this unit, in this this level of physics. It certainly was a possibility in the previous syllabus, but because it has to be standardized a lot more, it's fairly unlikely, I think, at your stage. But we'll see when the mock exams come out. But when I've used Ohm's law here, because I'm not talking about like my resistance doesn't have a direction, my current doesn't have a direction being applied to this, I just work out that the voltage being used going through it must be equal to 2, and I have to interpret that, yeah, that's the voltage, that's the change in voltage, must be negative 2 in this case. You have to use a bit of context knowledge in order to interpret whether these things need a negative or a positive sign on it. So we've worked out the change of voltage must be equal to 2 volts. And then finally, last bit is VC, the voltage in the current, or voltage in the, the voltage at C. Well, the voltage at C is just going to be equal to this 2 volts, or we kind of worked it out here that, well, from 0 to A we gain 2, from A to B we gain 6, we've got around here we lost 6, and so there must be 2 left over. That's all that it's asking about. Okay, let's move on. For this one, I've got the question here. I'm going to show you the figure because it's quite big, and then I think we'll see what we need to do. Figure 9 shows a circuit containing a simple network of 3 resistors connected to a DC battery of 12 volts. That's a fairly important number. Use circuit laws to calculate the readings on, we've got 2 ammeters, A1 and A2, and a voltmeter. So let's have a look at the picture. Okay, so here's our voltage. It's going to go this way through resistor 1, get down to here, split up. The fact that the voltmeter here is saying, yeah, it's connected to here and here, really doesn't matter. They could have drawn it connected to here, and it would have been the same thing. It's just it tends to get drawn like this to keep things neater and simpler looking. What is important for you to recognise is the voltage being used by R3 will be equal to the voltage being used by R2, because 2 objects in parallel will use the same voltage. So at X it splits up, goes into these 2, comes back together at Y, and then flows back through the ammeter at number 1. So let's have a look. We have few resistors. The best thing to do if you've got resistors and you know those resistance values is work out what's your equivalent resistance. Sometimes the question will ask you for it, sometimes it won't, but it's nearly always needed. So here we have 2 resistors in parallel. That means that we need to use 1 over RT equals 1 over 10 plus 1 over 10. I'm not going to write out the laws fully before putting in the numbers, I just don't have the space, but hopefully you guys are keeping up okay with that. So if we add those together, we get 2 over 10. So 1 over RT equals 2 over 10. So RT equals 10 over 2 equals 5 ohms. And it is important to recognise if you have 2 resistors in parallel, doesn't matter what they originally are, your final result will always be less than either of them, because what we're basically saying here is that it's easier to go through 2 things in parallel than to go through just one thing on its own. Okay? More electricity will always go through. So if this here is equal to 5, can't I write it, let's just use the number, then this plus this, the resistance total of the circuit must equal 20 plus 5 equals 25 ohms. Okay. And now we can start using our Ohm's law to work out the total current of the circuit, which in this case will give us A1, because A1 must be measuring the I of the whole circuit. Yeah, it splits up here, but it comes back together and then it rejoins. So, I of our circuit equals V over R. We're told V from the question, 12 over 25, and I would leave it at that. You can't reduce the fraction. If you turn it into a decimal, it's just going to be something a little bit below 0.5. And it gives us a nice 0.48. At least it's not a repeating decimal. I would recommend, if you're doing questions like these and your current gives you some sort of repeating decimal, feel free to write that for your answer for the workbook, but then go back to keep using the fraction as your calculation value, because it's likely that your fraction will simplify and then you won't have as much error in your final answer. But we've worked out A, so we've got our 0.48 amps. Okay, let's move on to B. So, we have here, B is A2. We know the resistance, but we don't know the voltage, we don't know the current. We know the total voltage is 12, but we don't know how much voltage this is getting used up. So, one way of doing it is to use our resistance. We know that the equivalent resistance for this area would give us the voltage. In fact, we're going to have to work this out the other way around. It has here, there's 2 ways of doing it. We've said here work out the voltmeter as C, but I reckon it's going to be easier to work on the voltmeter next and then work out the last ammeter. But there is a sort of tricky way to do it. The current going through them is equal to 0.48, 12 over 25. Both of those have the same resistance. They have the same voltage. We don't know what that voltage is, but we know it's got the same voltage. So it stands to reason it should have the same current. Let's work that out mathematically. V of 3 equals V of 2. So I of 3 R3 equals I of 2 R2. And we know those two values, so I3 times 10 equals I2 times 10. So in this case we can see that I3 equals I2 because the 10s will cancel. You could do this with anything. It doesn't have to only be a situation where they are equal to each other. You can use this for anything. We also, because of Kirchhoff's junction law, know that I3 plus I2 equals 0.48. But we've just said that they're both the same. So therefore, 2 times I2, I'll just use I2, equals 0.48, or that I2 equals 0.24 amps, which is the answer to our second question there. So you can logically work your way out to it. The other way I had it was thinking about is I could work out the voltage first, because that's going to be easier, and then use Ohm's law to work out the current. So if I know how much voltage this is using up, and so that's going to be equal to 20 times 0.48, and I could take that voltage away from that, whatever's left would give me there. Okay. I'll leave you to work that out that way. Then, well, now we know the current here. We know that voltage equals IR, voltage equals 0.24 times R was equal to 20, is equal to 10, so that's going to equal 2.4 volts. Okay. But as I said, if you work out the voltage being used up on this, V equals IR, you've got R, and we've got I to work out voltage, then subtract it from 12, you should get 2.4 as well. So give that a shot, see if it's right. What I do want you to learn from this, apart from seeing examples how to use these skills to solve a problem, is do not look at this list of going, oh yeah, A, B, C, and go, I've got to do it this way. I've got to go A, now I've got to do B, and now I've got to do C. Because, I mean, I looked at this and I first thought, yeah, I could use, I'll work out that one first for the current because I've got all the resistances, so I can work out the equivalent resistance. But then I'll use the voltage and the current to work out that to get me the voltage being used there. And then use that voltage to work out the current. And then go back and fill out, oh, yeah, well, there's the answer for this, there's the answer for this, there's the answer for this. It won't matter what order you do these questions in. It's you can solve the puzzle however you want. Okay, and that's how I treat these. They're like just big puzzles to pick away one step at a time. Alright, let's have a look at another one. This is, you can see the colour of the question box has changed. This is from one of the end of chapter questions, as I recollect. For the circuit in figure 14, calculate the value of the resistor R and the voltage at point P. So, now we've got the opposite. Before we had the resistances and we needed to work out the currents. Now we've got the currents and we need to work out the resistances, because we can see here we've been given the current. I don't know why they bother putting that ammeter there, but we've got the current flowing here. We don't know the current going through these two, but we do have the current going through there. So, let's go the other way. We know that R, oops, sorry, no, yeah, there it is. Could help if I set pen. we know that R equals V over I, and that equals 12 over 3, so that equals 4 ohms. So that means the total resistance for these two must, or these three things, must equal 4 ohms. Okay, so RT equals 4 ohms. Now we have a 1 ohm in series with this parallel component. We're just going to call that R. We don't know what that is. So 4 equals 1 plus, I'll go RP for R parallel. So that means parallel must equal 3. Okay. That's the total resistance for those two things. And we know that 1 over RP equals 1 over R1 plus 1 over R2. Well, 1 over 3 must equal 1 over R, as I've labelled it, plus 1 over 12. Let's work that out. 1 over 3, take 1 over 12 will equal 1 over R. Let's see, 1 over 3 is the same thing as 4 over 12. Yep. 4 over 12 take 1 over 12 is 3 over 12, which would be 12 divided by 3 equals 1 over 4. So that means 1 over R equals 1 over 4, so R equals 4. So I'm going to write that up there, 4 ohms. Okay, even though the total was equal to 3, remember, even if we add 2, doesn't matter what these two are, it will always be lower than the smallest. So we can see that this had to be just a little bit bigger than this. Now, I am actually going to erase the working out here just so that I don't lose too much working space. You might be going, wait, but the total was equal to 4, so how can this unknown here also be equal to 4? This plus this 12 lowers this by a small amount, but then we're adding that 1 back onto it. Okay, so I'm just going to get rid of that. Unfortunately, this device does not have a nice fast way to remove all these pen markings without losing a heap of our work. Now, there are some other ways to solve this. You could have used like Kirchhoff's laws, and going that, well, the current I2 and I3 must add to equal 3, the voltage being used up, because we know what the voltage, the current times this resistance would give us the voltage being used up here. We know the resistance being left over. In fact, we'll have to do that in a second anyway. So we could have done B first to then go back, but it really does depend. R of R was also equal to 4 ohms. It really does depend on what technique for the puzzle you see first and want to have a go with. So, a couple of ways we could do this. We could work out the current and then work out the voltage, but that seems like a lot of work. I know that here this has 3 amps going through it as well, so the voltage there equals 3 times 1 equals 3 volts. So if 3 volts is getting used up by here, that must leave 9 volts, because the total must add up to 12, being left over there. I'm going to show you another way we could have worked out the resistance, because maybe you saw how to get the voltage first. Great, so work out the voltage first. It's not going to cost you marks on the exam. Just make sure you clearly label what you're working on. But if we have 9 volts being used up on here, we could work out the current going through there. So I'm going to work that out. I equals V over R equals 9 over 12, so I would equal 0.75. That means, so this has 0.75 amps, so this means here must be 2.25 amps, and we know this because I2 and I3 Both come from I1 here, and Kirchhoff's current law says the sum of them in must equal the sum of them out. So the sum in equals the sum out. So 3 equals 0.75 plus I, so I would equal 2.25 amps. And we know it also uses 9 volts. Remember, the voltage is the same. So the resistance equals voltage over current equals 9 volts divided by 2.25. And 2.25 and 9, yeah, go 4 times. Equals 4 ohms. Okay. There will be multiple ways to solve them, and the unfortunate, and look, this is actually good for all your math problems, your physics problem solving when it comes to these sort of mathematical analysis type questions. The more you do, the easier you'll find it to do solutions for any of the problem sets. It doesn't matter that this is electrical circuits and then you go to heat. Getting good at solving problems will help you for all of them. It'll help you for your math classes as well. It'll help you for your chemistry classes as well. Biology, I don't know how much math you're doing in biology in terms of calculation type stuff, but it might help a little bit there as well. So the more you practice these, the better you will get for all of them. It won't just be for physics, but it'll be for all of them. Okay, here's another one, pretty similar, but now in this case we've got the resistances again, and we don't have the current. It has been quite nice in giving us a sort of suggested path in that, well, what's the total resistance? Now work out the currents, and then work out the voltage at the other end of it. So I will just do one quick label on here. I1 is also the same thing over here. Okay, the current going through that 6 ohm resistor will be the same as the current over here, just coming through that ammeter, because it's on a single line. There's no parallel components for it. The current will be less for these two because it's after a junction. However, once they come back together, remember the current will be the same. So what's the total resistance? So let's work that out. We need the resistance for these two. 1 over RT, what was that? One over RT equals 1 over 9 plus 1 over 3. 1 over 3 is the same thing as 3 over 9, so that's going to equal 4 over 9. So RT will equal 9 over 4. That's for the parallel part. I'm going to call it RP. But that might even be a better symbology for us to practice using. But RT will equal RP plus this bit that's left over, 6. Let's see, so if we put it all in fractions, 6 would be equal to 24 over 4. So 24 over 4. So 9 over 4 plus 24 over 4 would equal 33 over 4. Okay. 9 over 4, what's 9 over 4 equal to? 9 divided by 4. I mean, 9 over 4 is just 2.25. So we could rewrite this as 8.25. At least it's a whole decimal. Okay, sometimes it might be nice to... look, I just like working with fractions. I find them easy. You might like decimals, it's up to you. It's not really going to be a problem. Okay, now we need the currents. So we know that here the voltage being applied to this point is 8, and the total resistance for this thing is equal to 8.25. So current equals voltage over R, current 1 equals 8 over 8.25. So that's going to be a bit under 8 divided by 8.25. Ugh, repeating decimal. That's why I don't like using it. Okay, I'm going to just go back to using fractions. And the answer will be a fraction, but that's okay. fractions are our friends. 33 over 4, which means it's going to be 4 times 8, 32. 32 over 33. And we can leave it at that. I mean, that's also equal to 0.969696, so 96 recurring. Okay, is equal to 0.96 recurring. Remember, if it's 2 digits recurring, put a bar over the 2 digits. Better put a unit. Amps. So we've got our I for our total thing. Now we need to know, well, what is our I's for these two sections. So let's start with a bit of logic. Last time we did this, we had two 10 ohm resistors. Now we don't. Obviously, a lot more current is going to flow through here than here. This is smaller, this is bigger. How much bigger? Well, this is 3 times bigger than this one. So for every 1 ohm going through here, 1 amp going through here, 3 amps will go through here. Now we only have 0.96 amps in total, but the ratio is still the same. So the ratio of 1... my pen is not cleanly picking up tonight. It is a ratio of 1:3 in terms of how much current. So I can do the same thing I did last time, and I would recommend you do that. So voltage of 2 equals the voltage of 3. We know from Ohm's law V equals IR. So I2 R2 equals I3 R3. I2 times 9 equals I3 times 3. And you can see this time it's not going to cancel out so easily. We're going to divide both by 3, and we'll have that 3 lots of I2 equals the current going through I3. Okay, but the numbers are the opposite way. I'm saying 3 times the amount here for 1 lot of here. 3 times this equals 1 amount of this. Okay, this is talking about a proportion of how much is going through. This is talking about, well, if I take this number, I have to multiply it 3 times to get the same as this number. But we also know that I2 plus I3 equals I1, which was 32 over 33. Now I'm going to clean up a bit of working here. Let's see. I'll leave that there. I'll just get rid of this working. So we have up here that I of 1 equals 32 over 33. But we know that I3 is equal to 3 lots of I2. So I2 plus 3I2 equals 32 over 33. Or that 4I2 equals 32 over 33. When we divide, we just need to worry about dividing the denominator by it, and dividing 32 by 4 will give us 8. And I will leave you to work out the value for I3 by using this relationship here. Okay, so now we've got our two currents. And the last thing we need is our voltage. We could use any of these. We know what the current is equal to, and we can multiply that by the resistance to get the voltage. In fact, that's pretty straightforward. V2 is equal to I2, which is 8 over 33 times 9. 8 times 9 is equal to... Say times 9 equal to... I'm having brains 71. 71 over 33. And I will convert that to a decimal for a second. 71 divided by 33 gives us 2.15 recurring. The reason I had to do that is this is how much voltage is getting used up by either of these two rungs. So what's left over at X has to be equal to 8 take away 2.15, which would equal 5.85 volts. Remember, Kirchhoff's loop law says that the sum must equal 0. Positive 8, negative 2.25, whatever is left over must be before it gets used up here. So this X value here is before here. Okay? If the current had been flowing the other way, we'd have to take away the 5.85 to get the 2.15 left over. So the direction of the current can be important to take care of. Okay, how many more examples did I put on this? That's right, I put a few examples on. Where will we up to? Ooh, apologies for that. There we go. Okay, here we have another circuit. We've got to calculate some currents, and we need to calculate two voltages. So we will see something a little bit interesting about the question part B there in a second, but we will get to that momentarily. Notice it doesn't tell us anything about the resistances here. In this case, we kind of expected, well, you're going to need to do it, but we're not going to ask you to do it. Note, if something asks you to work out, say the current, but doesn't actually tell you to work out the resistances, you don't have to. There are tricky mathematical ways around it using Kirchhoff's laws. So you could use that if you wish to, because we could write a couple of simultaneous equations using voltage loops. We know what the resistances are, and we know some laws about the currents, so you could do that, but unless you're really feeling comfortable with the math, don't bother about it. It's only really a good thing to do if you don't have a lot of information. It can be quite helpful when you're dealing with very complicated situations, but this is not a complicated situation. It's basically the same as the one from actually it's pretty much the same as the last question. So we're going to do the same things we did last time. I am going to work through the resistances a little bit quicker. So the total resistance is going to be a parallel bit. So we're going to need 1 over 2 plus 1 over 6 equals 1 over RP. 1 over 2 is going to equal, what's that, 3 over 6, so that's 4 over 6. 1 over RP. So it's going to equal 6 over 4 plus, and we've got a 4 left over. 6 over 4 is equal to 1.5, so that's going to equal 5.5 ohms. Check my working. 1 over 2 is the same thing as 3/6, that's 4/6. 6 divided by 4 goes in 1.5 times. Yes, fantastic. And I'll just get rid of that work because we won't need it. Apologies. Okay, let's start working out the current. We know that the total voltage is equal to 6. We know the total resistance is equal to 5.5. So the total current, V over R, is our 6 over 5.5. That's a little bit of an ugly one. Let's see if that gives us a nice easy thing, or if it's going to give us a horrible it gives us a horrible decimal. Of course it does. Let's convert that into a nice fraction. That's 12 over 11. 1 and 1/11. Yep, 12 elevenths. Great. So there's our total current, which is 1.09 amps. Okay, we're going to do the same thing as before. We know that the voltages for these two must be equal. In fact, it'll equal Y there. And so whatever the Y will be equal to whatever that voltage is taken away from the 6. And then we can go, well, what was I saying? Voltage is the same, so we'll use those two to work out that, and the fact that they have to add together to equal this one to do the same thing as last time. So, V2 equals V3, I2R2 equals I3R3, I2 is equal to unknown, times 2 equals I3 times 6, so I2 equals 3 lots of I3. Then we know that I2 plus I3 equals 12 over 11, and let's substitute that in. So we're going to have that 4 I3 equals 12 over 11. I3 must equal, divide that by 4, we're going to have 3 over 11 amps. I'm just going to leave it as that. Okay, we are going to need I2. We know that I2 equals 3 lots of that, so that must equal 9 over 11 amps. Cool. Now, the two voltages here look tricky, but they're actually pretty straightforward. Let's think our way through. Kirchhoff's first loop. Leaves here, gains 6. Comes along here, goes through here, uses up some voltage, comes back here, uses up some voltage, comes back. Cool. Kirchhoff's other loop. Goes through here, gains 6 volts, loses a bit, comes back, loses a bit, comes back. So note from here, from Y to Z, on that first loop, it didn't actually lose any voltage. There's no element here between Y and Z. So it doesn't matter that the two loops have not rejoined yet. It doesn't matter that it's separate. The voltages will be the same. Now, in a reality, that's not true, because wires do have resistance, but we pretend that they don't have resistance for the sake of these problems, just to avoid dealing with that issue. So for us, yep, that used up some voltage. So this point and this point has a difference in voltage, but this point and this point, that point and that point, that point and that point, that point and that point, that point, that point, that point, all of those have the same, because nothing's happened. It doesn't matter that they come back together, that doesn't change voltage. It's still the same voltage. So we just need to work out the voltage being used up by one, and we've got both. We'll just use, let's see, we'll use the 3 over 11. We know that voltage equals current times resistance. The current on I3 equals 3 over 11 times 6 equals 18 over 11. And so the voltage starts off at 6. We're going to use, as good an arrow as that was, that's not what I wanted. Should be 11. 6 take away 18 over 11 equals, well, let's chuck that in, 6 take away 18, oops, 18 over 11 gives us 48 over 11, which is equal to about 4.36 recurring volts. Okay, so this last little hop here, that point Y has 4.36 volts. Yes, 18/11 of a volt, that's a bit over 1, or so 1.6ish, about 1.6ish got used up here. So there's 4.36 left over, but nothing got used up between these two, so there's still 4.36 left over. Okay, hopefully that makes sense. Sorry, I'm used to talking so much. just being cranky tonight. Okay, this is a reasonably complicated looking circuit, just because there's all these different paths that you can see. But this is exactly the same as the last three questions. We have a battery, it comes along, it splits up into two different points, comes back together, goes through this, comes back. The fact that there is a voltmeter here doesn't mean anything. In fact, we could have redrawn this as the voltmeter connecting up to there, so that we can say, oh yeah, the voltmeter is just parallel across that. They've just done it like this because it makes it look really sleek. That's it. It's just stylistic. Okay? Same way that this voltmeter 1 could have been attached to either side, or it could have been attached just to here and here. They do it like this so that it looks more modernistic and sleek. It's a stylistic choice. It can be kind of aggravating, but it's not anything we haven't seen before. It's just drawn differently. We have here some information. The battery consists of 3 cells each of 1.5 volts. So let's see what our question is. Remember that there was a line coming underneath that, but I had to put the bit over the top of it. We want to know what is the circuit current, what is the voltage reading, what is the current reading, and what is the battery EMF. I'm going to start with question D because we need the voltage before we really do anything else. The battery EMF, the EMF stands for electromotive force, how much it pushes the electrons, is the voltage. So D is just 3 times 1.5, because we're told each cell is 1.5, so that means 4.5 volts. And we're done. So D is pretty easy. That's what I mean by sometimes when you do these questions, as you work through it, you'll find that you've solved later parts just because your strategy happened to work a little bit differently. I'm honestly completely uncertain, because I'm 100% confident that you could not work out A, B or C until you had D. And I think, because this comes from the example questions, that's actually what Walding does. He works out the voltage, and then when he gets to D, goes, oh yeah, and the EMF is just the voltage. So, let's skip that and just jump straight to the end. We want to know now, what is the circuit current flowing from the battery? So what's the total current? Again, we need equivalent resistance. We've got 2 things in parallel, and then we've got 1 thing in series. So 1 over 10 plus 1 over 5 equals, 1 over 5 is the same as 2 over 10, so 3 over 10, so that here is equal to 10 over 3. 10 over 3 plus 5, so RT is going to equal 10 over 3 plus 5. I am skipping a couple of steps on my working out. I would really expect a student to show, oh yeah, RP, so therefore RP equals 10 over 3, just to make sure whoever's marking you is good on communication. 5 is the same thing as 15 over 3, so that's going to equal 25 over 3. And now that we know the voltage and we know the resistance, we can work out the current. So I'm going to get rid of that working out there in the middle. And I'm just going to write down that the RT equals 25 over 3. So this is a big question. RT equals 25 over 3 ohms. So, I equals, come on guys. I think I need a new tablet. I should fundraise one. So it's as frustrating as it is for you. So current equals voltage over resistance. Voltage is in this case 4.5, which should be the same as, let's convert it to decimal, 9 over 2. And this is why I like 9 over 2 divided by 25. Oh, come on. 25 over 5. So, when you divide by fractions, you multiply by the reciprocal. So that's going to be 9 times 5. 9 times 5 is 45 over 50, which is just going to be a nice easy 0.9 amps. Let's see, 10, yeah, 9, yep, great. And that's why I like working with having the fractions there as an aside, because if I'd worked with 4.5 divided by you're probably screaming at me in the background, that is not a 5, Mr. Warren. That is a 3. And it is my terribly bad. Yeah, it's not, the damn nib is not releasing. And it is just your terrible handwriting. What was that? Compounded with the fact that the pen is being stupid today. That is causing these issues. So, the numerator was fine, 50, but 3 times 9 is 27. A little bit less of a nice fraction. 27 divided by 50 gives us 0. Oh, that's a good decimal. 0.54 amps. Cool. Okay, well there's part B. Let's have a look at the current on ammeters A1 and A2. So A1 and A2, we can see they've split up. So we're going to do the same thing we've done in the last couple. The voltage is the same. Don't know what it is yet, but the voltage is the same. So we can now use those to work out the currents. V on 1 equals V on 2. I1 R1 equals I2 R2. I1 times 5 equals I2 times 10. So I1 equals 2 I2. And we know that I1 plus I2 equals IC, which we worked out over here. I'll put a C next to it. So 2 I2 plus I2 equals 27 over 50. So I2 will equal 27 over 50 divided by 3, which is going to equal 9 over 50. And so that means I1 must equal 18 over 50. Okay, I'm going to have to get rid of that working out in the middle, but we've seen the exact same process used several times now. So now we've got our 2 ammeters solved for part C actually. We don't have our voltage solved yet. A couple of ways we could have actually. I'll show you how I could have worked out the voltage before working out. What's what I'm looking for? Before working out the ammeters. You've seen in the last 2. Oops. You've seen in the last couple of videos where, having worked out the current, we've gone and worked out the voltage being applied to it. I'm going to go the other way this time. So, I know that the current here, we can see IC is equal to 0.54 going through here. We know the resistance, we know the current, we can work out the voltage. So the voltage equals I, which is 27 over 50 times 5. 27 times 5. Let's see, 20 times 5 is 100, 5 times 7 is 35. Yep, so that'll be 135 over 50. Actually, no, let's just use some simple reduction. 50 is just equal to 5 times 10, so this will equal 27 over 10 volts. But I'm going to probably need a, well, that's an easy thing, equals 2.7 volts. And we know that 4.5 volts is what's coming out of the battery. Since 2.7 gets used up here, this has to be equal to 4.5 take away 2.7, because we know this is giving off 4.5, this is using up 2.7, so the last bit left over must be going there, and that's going to be equal to 1.8, so V1 equals 1.8 volts, and that must be equal to V2. Having got this, and since we know the resistance on each of these, we could have actually worked out A1 and A2 using that. You can see in this case I just skipped C and skipped B and went straight to C, because again I was looking at parallel circuits, I knew the current going into it, and we'd done 3 of these questions just like it. And that's what I mean, it doesn't matter what order that they give you. If you have a question where you have 3 or 4 unknowns, A1 of currents, ammeters, voltmeters, or resistances, just work them all out. Okay? Obviously don't work out stuff you don't need to work out if you can avoid it, but once you've worked out the things you know you need, you've probably got everything solved in order to answer every part of the question. And I think this was our last one. This is a nasty one, and this is a nasty one because it is a this is a 3-star question from I believe the complete end of the unit review. And these sort of things, they're not completely what's what I'm looking for. They're not all that difficult, but they do take a few steps to get to where you want to get to. So let's have a look at this. We have our volt, and we're told that it has, we don't know what the voltage is on it. We know that there's 1 amp of current coming through here, and we know that there is some voltage being applied, and we know all the resistances, but we've got to work out what's going on. So let's think about the loops. We have the voltage, comes out here, comes through here, comes through here, and it can go through here or back to here, or it goes through here, back to here, or through here, then back through here. So these 2 bits are in parallel with each other, or this bit is in parallel with these 2 bits, and that's going to be really important in a second, because we're going to need to work out the equivalent resistances. But so these 2 in series, are parallel with this, then this chunk here is in series with this, then all this chunk here is in parallel with this, and then this big chunk here is in series with these 2. So there's a heap of things going on here. I'm not going to draw every step, because if we draw every step, it's going to double the length of the video. But I will talk my way through as we go through each one. So these 2 here, they're going to sum up to 30 ohms. They're in series with each other. So I'm just going to write here 30 ohms. And then I have a 15 parallel with a 30. So 1 over 15 plus 1 over 30 equals, well, that's 2 over 30. Plus 1 over, that's 3 over 30 equals, so therefore the RT, or the equivalency, must equal 30 over 3, which is 10. So the whole thing here equals 10. Whew. Okay, Well, the next step's nice and easy. 10 plus 5 gives us a 15, but that 15 is parallel with a 60. 1 over 60 plus 1 over 15 is going to equal, well, 1 over 15 is the same thing as 4 over 60, so it's going to be 5 over 60, and 60 divided by 5 is 12. So then this whole thing, plus that, is equal to 12. And then this 12 was in sequence with these two, which is just add them together. 80, so 40 plus 40 is 80 plus 12. So the total resistance is 92 ohms. And this looks ugly, but all we did was apply the same thing 3 times. You've just got to take it really slowly and think your way through, okay, well, I've got this little bit and these little bits, and simplify it step by step. Okay, but how do we work out the voltage that's going across here? Well, let's think about this, because this is actually really a lot easier than it looks. The voltage drop going across this must be the same as the voltage drop going across that, or that whole section there, because remember, this whole section here, that bit that equals 15, was parallel with this. Okay, that's not too bad. And this voltage, this bit here, is parallel with this. So if we know the voltage going through these, then we know the voltage being used here. And then, since we know the voltage being used, we know the current. And since we have the current, and we know the current here, we could work out the current going through here, which would let us work out the voltage being used up by it. And if we've got the voltage being used here, and the voltage being used here, or here, because remember, these two bits are parallel to that bit, then, because we've got the voltage for this whole bit, we know that the voltage for that is there. In fact, I think the next step for this question was in the previous textbook, well, what is the voltage actually being created by the battery? So, let's start right here at the very top. This bit I'm going to show as much working as I can. Here I have 30 ohms, R equals 30, I equals 1, V equals IR, 30 times 1 equals 30 volts. That was easy. So that means for this bit, that has to have 30 volts as well. V equals IR, I equals 30 over 15 equals 2 volts. Okay, so this bit here, sorry, 2 amps, not 2 volts. There. That had 2 amps going through it. That bit here had 1 amp going through it. 2 amps plus 1 amp means that this has, this 5 ohm resistor here, 3 amps of current going through it. But we want to know, was the voltage being used up by that? We have, again, going back to the same thing up here, V equals IR. We just worked out the I was 3. Okay, so I equals 2 plus 1 equals 3. So we've got 1 from here, 2 from here that we've just worked out equals 3. So 3 times, better be done soon, times 5, that's going to equal 15 volts. So we have 15 volts being used here. We had, how much voltage? We had 30 volts being used here. So the total voltage being used up was 45. Well, if that whole bit there was parallel to that, and that equals 45, therefore that must equal 45. So, your activity, and I don't have a heading for that unfortunately, but you've seen several examples now. I want you to reflect back and jot down to yourself 3 things to remember whenever you do a circuit analysis problem. So these could be some steps. For example, can you make an equivalent resistance? Or they could be a sequence of steps to do. Try this, then try this, then try this. Okay, something that's iterative. That means you can just keep looping back through it. Look for this, look for this, look for this. Cool. Now go back and start again. Look for this, look for this, look for this. You'll see that, especially for that complicated problem, I just had to keep doing the same thing again and again until finally I got to where I needed to be. And you'll find that some questions are like that. So, this video, we've gone through a couple of following. We've learnt how to draw different elements for circuit analysis, and we've learnt how to apply different electrical laws to solve for unknown values. Now, for your entrance slip to class, I'd like you to complete questions 1 to 6 in Chapter 9.2 Check Your Learning, and put that into the 3.2.5 space on eLearn. I know that was a very long video, guys. Thank you. If you listened to the whole thing, thank you very much, and I'll see you next time. Bye.